Feel good? Next step, crank the derivative of this. Y sub b double dot is equal to the acceleration of b is equal to minus half of the acceleration of a, y sub a double dot. So there's an expression to answer the question in general. I'm sorry, that should be A over here, shouldn't it? Yeah. Okay. And so then we can put in the values here. So the acceleration of B minus 1/2, and in the question, you mentioned it. If the velocity of block A is up the incline, is increasing at a rate of 0.044. So the acceleration of A is up the incline. So what do we do? What do we have to do? We have to assign a negative, doesn't it? Don't we? We have to assign a negative because of the way that we have defined the kinematics here. We've defined the kinematics, positive sense in this direction. They told us that this body is accelerating up the ramp, causing the acceleration to oppose this. So you have to be very careful to assign a negative there. So you do that in here, drop it in, and you get the acceleration of B then is equal to positive 0.022 meters per second squared. Which means it is going, accelerating downward. When we started class today, I was picking on you about English comments. Here you go. Okay? Accelerating downward. You know, instead of just cranking the math, try to add some English comments. Matter of fact, you could add other comments, and in the interest of time, I oftentimes don't do it here in class, but you could write a little comment or two over here that if body A is moving down, then body B rises. You know, little things like that to give you a little insight, and this relationship indicates that. Okay. Let's see if we can do another one that maybe has more than 1 degree of freedom.
Can I ask
Yes.
a question about
Sure.
on the sample problem on page 102? I'm just a little confused by why it was okay for them to just say that it was 3YB, the way the pulleys are set up.
Yes. Okay, so here's what Pam's looking at. This looks like a single degree of freedom problem. Okay. And so notice how they came off of the top locked-in pulleys here to define the YB and the YA. So if I was writing the equation for the length of this, I think what you're seeing is they're saying 3YB here, right? And so you're noticing a strand on the left, in the middle, and on the right, but they're not all the same as YB, are they? Everybody follow what Pam's question is? But they're over here in the book. Whoops, my finger won't quite get there. Let's see, I'm going to back out on the zoom a little bit. Look in the book right here. This is what they wrote. L equals 3YB plus 2YA. So the question is, what about these other two strands? Now, we're also making a simplifying engineering assumption here that this strand is effectively at a very small angle off the vertical, so we can ignore the fact that it's actually slightly tilted off, second order type of effect. Why can we use 3YB? And then, of course, 2YA over here is pretty nice. And then we got some constant stuff up here going around the pulleys and this piece of cable at the top.
That should work as long as the pulleys don't hit each other.
Right.
So that looks like there's a
But there's
constant.
two strands right here, right? Two pieces of that part of YB that are missing.
They're included in the constants.
They're included in the constants, aren't they? Can't you just back them out as part of the constants?
Then why
Like
would
Alfred
we
did?
define YB up to point C then?
It would have been.
We could have.
It would have been equally legitimate to do that. Just
Yep.
right there.
And
Yeah.
that was a good observation. That's the way I probably would have done it. And probably the way you would have done it,
And then
right?
consider the part above point C as a constant
And
because that's
then
what it is.
all this wrap from above here, all of that up and over the top until you get around to right here is going to be constant, all of that. Yeah. Okay? So you have some choices there. Now, rather than me taking time to teach this, because usually I do these kind of problems the way I just showed you by writing a length of cable equation, but I want to illustrate to you that there's a second way you can do these. And they've done that nicely here. You can use differential displacements. You can use differential or imagine infinitesimal displacements occurring. For instance, imagine that body A here is lifted. Well, let's see, what have they done with it? Well, it's going to be, I'm going to do something slightly different than what they appear to have done. Imagine that I lifted body A is going up while body B goes down. What if body A went up a microscopic amount? Wouldn't it essentially be hinged on the left edge here? And I think what I should do is go ahead and draw this on the board. If I took a look at that, here's body A in that example. This cable's coming down from up above where it was fixed. So this point acts as a pivot point. A pivot point. And as this body on the left is getting drawn down, it's going to cause this point over here to rise up by some amount, pivoting off of this point. So what we end up getting is a displacement, some delta here.
Did you say that A goes down?
No, I don't know what I said. Sometimes my brain doesn't work the same as my hands. If I'm pulling body B down, body A will rise. And the way body A would rise is by the cable lifting up over here. And this point would act as a pivot. Is that okay? Yeah. And so that means that this thing then would rise how much proportionally compared to that delta?
Half.
Okay. Half as much, right? So this vertical displacement right here of A would be half as much as that. Okay? Now, if you follow that, if you track that cable back around onto the other pulleys in the system, you can then apply this same kind of differential displacement to those other pulleys, and then you can write a relationship between the delta here and how it relates to the delta motion, the vertical motion of the other body over here on the left, which happened to be body A rising up. I'm sorry, pulling down. Body B pulling down, body A going up. So you'd just write differential relationships, and the book does a nice job laying that out with the different pulleys here. And then they come up with a differential relationship down here in the book, if you can track that. Now that can get quite complex for several degree of freedom problems. So that's why typically I avoid that approach. Okay. But be aware that this approach is useful at times. And this could be in a manufacturing situation, easily in a manufacturing situation or in some other application. Okay. In civil engineering, most likely. Okay. let's do a multi-degree of freedom problem.
That large pulley,
Excuse me?
that large pulley in that example,
Mm-hmm.
why isn't the differential amount that it's changing and subject to the origin of the circle? I don't get why it's offset like that is.
I'd have to track this thing carefully. What they've done here is they have body A moving, here's body A over here moving downward. This amount, which is half of the rotation, or half of the cable length here. And then this piece is then going to carry up and over, down to here. So what we have to do is we have to match this piece, this 2ds sub A here, with upward motion on the left edge of this pulley over here. Okay? And then let's see if there's some other thing we can track.
It looks like they're just doing that to graphically represent the fact that one line is sort of kinked, and they're just trying to straighten that out.
Well, what they're doing is they're showing that this piece here connects to this piece through an opposing for inextensible cable. Has to be. And then what's going on here is this particular pulley right here is rotating about its center, so whatever goes up has to come down on the other side. That's then attached to the center of this one, which means that if this thing rotates a little bit, if this one rotates a little bit in this sense clockwise here, then this is going to rise up, which causes this center down here to rise up that same amount. And while that happens, the right-hand edge up here goes down, and that has to match what comes down here. You then have this offset, and there's a relationship that exists between these three items. Then you can write the equation, because this is what you're really interested in, is how does this center, S sub B, differential displacement, relate to the differential displacement S sub A. That's how they do it. So you can see it's a little more involved. It's a little easier for you just to write the cable equation.
Right, so in what instances would that be easier than, say, the cable? If there is any instances.
Usually not. Maybe on a single degree of freedom problem, it might be simplest to just use these differential displacements like that.
Okay.
If it gets more complex, just be aware, you might see a civil engineering instructor or something doing something like that someday, and you can pull out your old dynamics book and go back here to this introduction on this topic. Okay, let's grab another problem. Oh, let's see, we have a variety of them we could do. Why don't we do a 3 degree of freedom one, which I pointed out to you a little bit earlier. And I've already done some penciling on there. I'm going to go ahead and bring that in so it'll show up reasonably well. There we go. So what I did is I went through and I looked at this, and I said, okay, here's body C, so I defined Y sub C as shown. Similarly, body D, and then I came over to body B and body A. And then we have 3 strands of cable here. So then, if we start writing equations, and I actually penciled this out, go ahead and grab it. So looking at that picture, if we wrote strand 1, which I have labeled over on the right side there, strand 1's equation length, it looks like it's made up of y sub b plus y sub a plus, there's another little segment in there, yb minus y1. Because see, y1, the way I have that labeled, y1 is over on the other cable. So what I'm doing is I'm mixing a portion of a length that's over on the other cable. Now, anything else on that right-hand cable? We have y sub b from this pulley up to the top, and we have y sub a, and then we have y sub b take away y sub 1, right? Plus some constants. If we go to the next cable, labeled number 2 in the middle, it looks like it's made up of y sub c plus 2y sub 1, what I labeled y sub 1. And we're looking at cable 2, there in the middle. Y sub c plus 2y sub 1. What's missing?
That little portion between the pulley there on the left side of C.
Which is a y b minus y.
This piece
Yeah.
right here, which looks to me like y sub c minus y sub 2, doesn't it? Right? Y sub c minus y sub 2. Plus some other constant. Let's label those C1 and C2. Now what we'll do in a moment is, well, we'll get these equations written and then we'll start taking the derivatives on them to answer the question. Okay? Now we have the third cable over on the left, and that one looks like it's made up of a y sub d plus 2 of those things called y2. Plus some constants. Okay. Now, when we crank the derivatives on these equations, let's go ahead and do that. So this is 1, 2, 3. So 1 prime is going to give us 0 equals yb prime dot plus ya dot plus yb dot minus y1 dot. Our second equation, these are pretty straightforward, but the hard part is right here, getting this stuff laid out. We crank that, and we're going to get yc dot plus 2y1 dot plus another yc dot minus a y2 dot, and then finally a third equation on the derivative. 0 is equal to yd dot plus twice y2 dot So, what can I eliminate out of these three bottom equations? The question was asking, what's the relationship that exists between the velocities of the four different cylinders?
You get rid of y sub 1 and y sub 2.
Yeah. So we have three equations, so we could substitute and get rid of y sub 1 and y sub 2. So down here in our third equation, it implies that y sub 2 dot is equal to negative y sub d dot over 2 we could take our first equation and solve it for y sub 1 dot.
This is looking messy fast.
Like, well, kick this over to the other side, and we've got the sum of these three, right? And we have a pair of y sub b dots and a 1 y sub a dot. Right? And now take this equation and this equation and put them into our second equation, and we eliminated y1 and y2. So we end up with a pair of y sub c dots. We have 2 y sub c dot. Right there. And we have twice y sub 1 dot, which is up here, and twice y sub 1 dot doing the substitution is going to be twice y sub a dot plus 4 times y sub b dot. We took care of our pair of yc's dots already, and then to subtract off our y2 dot, which becomes then positive half of yd dot. So there's a relationship. If I would multiply both sides by 2, I could eliminate, or actually I could, might be simplest to divide both sides by 2 and just reduce that out of there. Looks like what they did in their solution in the book is they've just cleared the, they
half out of the
multiplied that through, right? Multiplied the half out. Okay, so here's the relationship that exists between the velocities. If you look back at that problem now, it gives you a relationship for this pretty complex system. All right. We have time for, how much time do I have back there in the studio roughly? No time? Okay. Okay, we have no time. Okay. So we'll go ahead and wrap it up for the day. What I'll do next time is we will answer questions that remain here, and then I think we might work another constrained motion problem, and then go ahead and get started on actual particle kinetics. Okay.